Good morning, everybody. So today is Monday, September 21st. I hope everybody had a good weekend. I hope you guys feel good after taking the test. I know it was extremely challenging on some parts. I apologize. We will go over it and we will learn from it. Um, and I just hope that the tests get easier. This one was not quite an AP test, but I would say that the free response was difficult. The multiple choice was probably pretty kind of easy for you guys, so I hope you guys did really well on that. And the grades should kind of balance out, and I will curve things, so that should be good. So here's our warm up. So if you were absent today, make sure that you complete the warm up, and I'll put the link on Canvas. So I'll post an assignment or an announcement for today's links and everything. So that'll be a Google Doc that I'll share with you. You open it and then complete it in there. Make sure that you change the link to Garland ISD. All right, and there's our answer key for that. All right, so that's the wrong date. That's okay. So today we're going to be reviewing concepts from Unit 3, Chapter 3, Stoichiometry. Hey, that rhymes. I'm going to show you guys a video for limiting reactant. We're going to actually give this to you guys as an Edpuzzle assignment, okay? And so it's an intro to limiting reactant uh, to kind of help with that. And it's kind of a fun video, and I like it. Then we're going to review over the Chapter 2 problem set answer key. So the Chapter 2, the last homework that I gave you guys on Chapter 2, which was our last homework assignment. And I had some students came to tutoring that were asking questions about it. So I'll try to address those questions. So in-class assignments today. So make sure you complete the warm-up. Make sure you participate in class discussions. And then make sure that you complete the exit ticket. Okay? And I'll give you guys the link to the exit ticket. Older assignments, make sure that you have completed the Unit 1 exam for response and multiple choice. If you have not completed that, please submit it. It is late. Average atomic mass homework was due the 21st. So that's due today. Okay. And this stuff kind of does stack up. So if you haven't done this one, please complete it really soon. Let's say by Wednesday, and I'll take it for full credit because this one might have fallen through the cracks. So if you can complete it by Wednesday, I'll give you full credit if you haven't completed it yet. NIMSY Notes number 3 was due yesterday. So same thing, if you can complete it very soon, I'll still give you full credit because I know you guys have been busy working on the test and other things. So I'll try to work with you, but we want to try to, with this virtual environment, it's easy for us to extend our deadlines for our assignments and kind of stretch things out, but that's not going to help us in the long run, so we don't want to get too far behind. I want to be flexible, but at the same time, we want to keep a certain level of rigor um, and just maintaining a workload that's appropriate for the class. We don't want to extend everything too long and then not complete things on time. That'll be a bad habit to start, so we don't want to do that. And I know there's a lot of work in this class. I'm trying to keep it easier than I usually do, but I'm still trying to make sure that you guys are getting the information that you need and that we're getting the skills that we need so that we can pass the AP test. That's our goal. All right, learning goals for today. So students should be able to convert from moles to moles using a balanced equation. So if you got so many moles of A, how many moles of B are going to be required to react, or how many moles of your product are you going to be able to make? And so that's all moles, mole to mole conversions with a balanced equation. So that's stoichiometry. So this is all stoichiometry. Convert from mass to moles using a balanced equation. So if you start with mass, can you go to moles of a different reactant or a different product in that balanced equation? Convert from mass to mass using a balanced equation. This one is actually another way to put this is so students should be able to convert from mass to mass using a balanced equation. Another way to put this is students will be able to determine the theoretical yield. So if you start with the mass of a reactant and you predict how much mass of a product you should make using the molar masses and all of our mole stuff conversions, and the balance equation, that's calculating the theoretical yield. So students should be able to determine the theoretical yield of a product that will be produced given a balanced reaction. And we're going to practice this with the lab. I'm hoping that we can start the pre-lab on Wednesday, and then we'll do the lab on Friday. And so I should be able to demonstrate the lab during class as long as I can get everything I need. So I got to go ahead and make my list of what I need next week. So today, tomorrow, and then by Friday we can do the lab. Y'all can see, I'll show you a video of us doing the lab. So that'll be kind of fun. Convert from moles to mass to volume. Oh, my dinner's here. Okay, I gotta hurry up and hurry this up because I gotta eat. Convert from moles or mass to volume. So if you're given moles or mass, can you convert it to volume of a reaction or product? Determine the limiting reactant and determine the excess reactant, and then determine how much is excess after reaction goes to completion. And if you guys watch the Edpuzzle, this is why I really like the Edpuzzles, because that part is tricky, and I've always had a hard time with determining how much is left over after a reaction goes to completion, and I was kind of stuck. It just didn't make sense to me when the first time I taught this class about 4 years ago. And I watched that video, the Edpuzzle that I assigned you guys, and it clicked, made sense, and I was like, yes. So I hope that'll make sense for you guys. Here's our mole conversion factors again. So 1 mole is 6 times 10 to the 23 particles or atoms or molecules. 1 mole is the molar mass or the atomic mass of that substance. And then 1 mole is 22.4 liters. I know we keep seeing this, but we need to keep seeing it because this stuff is critical. All right, what mass of ammonia, that's ammonia, NH3, is formed when 5.38 grams of lithium nitride reacts with water according to the equation. I've shown you guys this one before briefly, but let's go through it. So we are starting with mass of one of our reactants, and we want to know how much ammonia is formed. So ammonia is a product. Now notice that it doesn't tell us how much water is reacted, and so it doesn't matter. We just assume that we have enough water in excess so that the reaction can go to completion. All right, so we're just going to predict how much ammonia we can make given that we start with 5.38 grams of lithium nitride. Okay, if they told us both the lithium nitride and the amount of water we started with, if they said 5.38 grams of this lithium nitride and 5.38 grams of water, then it would be a different story. This would be a limiting reactant problem, right? Because then you don't know which one runs out first. In this case, it's not. So this is a simpler problem. So we're going to start with that 5.38 grams of lithium nitride and convert it to moles. So I know that 1 mole of lithium nitride is its molar mass, 34.83. And then I look at the balance equation. I go mole to mole. Okay, and we might want to double check if this equation is balanced. But if they give you an equation, and then if they give you this balanced equation, right, let's see. Let me word that a different way. If they give you an equation in a question, it's gonna be balanced. Okay, but you can always check just in case. But pretty much, if you are given an equation, it will be a balanced equation. And usually they use those words. Usually they'll say according to the balanced equation. They'll usually use those words, and then you'll know that it's balanced without having to check. So now we have moles of lithium nitride. And then from the balance equation, we see that it's a 1-to-1 ratio because there is no coefficient in either of them. That means 1. And then we need mass of our product. Now that we got moles of our product, NH3, we want mass. So we multiply by its molar mass to get that from the periodic table. And we get 2.63 grams of ammonia. So this is a theoretical yield. If you were to do this experiment and you started with 5.38 grams of lithium nitride and you did this reaction, you should be able to produce this much, assuming 100% of your 5.38 grams reacted, which isn't always the case. So you're likely to get less than this in a reaction because you're not going to be completely perfect and get it all converted. But you should get something kind of close to this, right? Maybe a little less with some error margin. Okay, and then when we do the baking soda lab, this is kind of what we're going to be doing. We're going to be predicting the theoretical yield for baking soda reaction. All right, so I hope that one's good. All right, the limiting reactant or reagent is the reactant that limits the reaction. It determines the amount of product that can be formed. So if you're given the amounts of 2 or more reactants in a stoichiometry problem, and you're asked to determine how much product forms, the easiest thing to do is to work a problem with each reactant and take the smaller of the two answers. So that's a really good tool. It's a really good way to attack this problem. Sorry, I gotta turn this off. It's my loud air conditioner. So if you're given two numbers, like that last example where you've got mass or moles of one substance, mass or moles of another reactant, and they both react in the balance equation, and then you asked how much of a product forms. Well, you have to take them both, figure out how much forms, and then take the smaller of the two, because your reaction stops when you run out of ingredients. Okay. So here's an example with this, and you'll see this in the video, the Edpuzzle that I was talking about. Let's say you must work in a sandwich shop. You must make sandwiches according to the following formula. You use 2 pieces of bread, 4 pieces of meat, 2 pieces of cheese, 3 pieces of bacon, and 2 ounces of special sauce. That sounds like a good sandwich. If you have 20 pieces of bread, 32 pieces of meat, 20 pieces of cheese, 21 pieces of bacon, and 1 quart of special sauce, how many sandwiches can you make? So this is a cooking question, but it applies to chemistry because it's the same kind of math. If you were to make sandwiches, you would have to figure out how many, you have to divide out each of your ingredients by, see how, you can see how many you can make. So this is pretty cool. It's kind of fun. Okay, here's the link to the video that I gave you guys for the Edpuzzle. And then here's some other links that I gave you guys, and I changed the background so that you could see this because it didn't show up on the other one. So limiting reactant practice problems, if you want to see some actual practice problems, these are really good. And then mole ratio practice problems, and then gas stoichiometry practice problems. And these are pretty short videos, and they're pretty helpful. This guy Tyler Windowit's pretty good. He's one of my favorites. So here, we'll do this one in class, okay? So how many moles of iron hydroxide, which is a solid, can be produced by allowing 1 mole of iron sulfide? That's going to be iron 3 sulfide, because it's a +3 charge there, if I do some mental math. 2 moles of water and 3 moles of O2 to react. So here's our balanced equation. We got 1 mole of this, 2 moles of this, and 3 moles of this. Oof. How much of this can we make? How many moles? We want moles there. Okay. Remember the trick? There is a trick where you can do this. You can take the number of moles of that you're given in the problem, divide it by the coefficient, get that number. So that's 1/2. So that's 1/2. And I'm going to try the trick right now. So that's 1/2 is my. Let's call it a factor. My factor is 1/2. It's going to be my number of moles divided by my coefficient. Number of moles divided by my coefficient from the balance equation. And let's try it. So I get a factor of 1/2 there. This is going to be 2/6, which is 1/3, which is less than that one. This is 3/3, which is 1. So which one of these is smallest? I would say the water. So I am predicting with this shortcut, with this trick, that the water is limiting. I'm not sure which one's limiting. Okay? Just to show you how to do that trick. So let's go ahead and try it. So 1, 2, and 3 moles, which I already wrote down. So we start with the 2 moles of water. Oh, I think it shows right here. Water is limiting. So if you actually go through the math of doing this, let me show you how to do the math to determine it. So you can do the trick, okay, and it saves a lot of time, and it is very valuable on the AP test. But let's look at each one. So we have 1 mole of this Fe2S3, and we know that there's 2 moles from the balance equation right there. And then let's see how many moles of our product we can make. 4 moles from this balance equation right here. FeOH3. So that's iron 3 hydroxide. So if we did that, that's 4 divided by 2, which is 2. Let's do the same thing with this guy. 6 moles. Oh, wait. We want 2 moles of water. And we know that there's 6 moles of water is required to react to form 4 moles of iron hydroxide. And I wanted to write on my iPad, but I did not bring the pen home, so I cannot do that. So that's 8 divided by 6, which is 1.33. So notice that the water is less. So the number of moles of iron hydroxide I can produce from water is less than the iron sulfide. So I know that water is more limiting than the iron sulfide. So I'm going to go ahead and erase the iron sulfide because I know it's not limiting. It's going to make more. And we want the one that can make the smallest number of moles and then smallest number of mass of the product. So let's do 3 moles of O2. I know that from the balance equation, there's 3 moles of O2 is required to react to form 4 moles, again from right here, of iron hydroxide. So what do we get there? 3 times 4 divided by 3. So that's 4 moles. That's even more. And so oxygen is not limiting. So water is limiting here. So you can do the shortcut, or if you want to be sure, you can do it this way. You can take the moles of each and convert them to the moles of the product. Now, once you know the moles of the product that you can theoretically make from each reactant, that is the number that you need to determine how much can be made. You do not have to multiply this by the molar mass of the substance. Because if I take 4 times the molar mass of iron hydroxide, that's still going to be more than 1.33 moles of iron hydroxide because the molar mass is the same. So once you have moles of the product, you are good. You do not need to go all the way to mass. Okay? So let's see how much we can actually make. So we can make 1.33 moles of iron hydroxide with the water, and the water is limiting. And I think that's all we needed. We didn't need mass. How many moles of iron hydroxide? So we can make 1.3 moles of iron hydroxide. So we start with the 2 moles of the water from right here, and we do 4 moles from here, 6 moles from there. 2 times 4 divided by 6 is 1.3 moles. So that's the fewest number of moles that we can make. So we'll run out of water first. We have plenty of the other 2, but we'll run out of water first. Excuse me. If 17 grams of ammonia were reacted with 32 grams of oxygen in the following reaction, how many grams of nitrogen monoxide could be formed? So what we need to do is, let me see if I had labeled it. Yeah. So we want to know how many grams of this we're going to form. So we take the mass of each reactant, divide it by its molar mass, and then do our trick again. So let's try that. So 17 grams of NH3. We're going to divide by its molar mass, which is 17. That's 14 plus 3, so 17 grams. So that ain't that nice of them. So that'll give us 1 mole of NH3. So we have 1 mole of NH3. And then we know that 4 moles of NH3 will react to form 4 moles of NO, of nitrogen monoxide. 4 moles of NO. All right. And I'm just going to get moles right now just to see. So 17 times 4 divided by 17 divided by 4. 1. Okay. We can make 1 mole of NO from this. So I'm going to write this up here. So 1 mole of NO from the NH3. Okay. Let's try our trick. Oh. So 17, we had 1 mole of NO of NH3, right? So let's take that, take the number of moles of that substance given in the problem. We had 17 grams. We figured out that that's equal to 1 mole because it's equal to the molar mass. So 1 mole of NH3 divided by the coefficient here, which is 4. And that tells us how many, that's our factor. Our factor is 1/4. All right, let's try our factor for oxygen, 32 grams of O2. Ain't that nice of them? That's the molar mass of oxygen. So that's, what am I doing? That's the molar mass of O2, so 32 grams of 1 mole. So that's also 1 mole of O2. Let's do our factor. What's the factor for O2? We have 1 mole of O2 divided by its coefficient, which is 5. So that's 1/5. So it looks like oxygen is going to be limiting. All right. And so let's see, how do we determine our answer? So now that we know that oxygen is limiting, let's go ahead and convert 32 grams of oxygen to grams of NO, and we'll see how much mass is required, because we know that that one's limiting now. There we go, 17 grams. So this is the mass produced from each. And so notice that the oxygen produces less. So we will run out of oxygen first, and we'll make 24 grams. So the way that we did that is 32 grams of O2 is what we were given, divided by the molar mass. The mole ratio is 4 to 5. 4 to 5 right there. And then the molar mass of NO is 30 from the periodic table. So we get 24 grams of nitrogen monoxide. Beautiful. 24 grams is a smaller yield, so O2 is limiting, and 24 grams is how much we'll be able to make. The theoretical yield is the amount of product that should form according to a stoichiometric calculation. So we'll do a lab here in a little bit where we calculate the theoretical yields, and so that we should be able to do that pretty easily now. Actual yield is the experimental yield. That means, what did you get in the lab? You did an experiment. What did you get? How many grams were measured? Percent yield is how much you actually got in the lab divided by the theoretical maximum that you could have made times 100. Okay. Is the reaction of 1 mole of CH4 with an excess of Cl2, 83.5 grams of CCl4 is obtained? What is the theoretical, actual, and percent yield? Okay, so we start with 83.5 grams of chloroform, carbon tetrachloride. That's our actual yield. So that's how much we actually made. Let's go ahead and calculate our theoretical yield first. So let's look at our steps. Calculate the theoretical yield first. Then second, we're going to find the percent yield. Okay. Oh, I always spell that backwards. I before E. That's funny. All right, so here's our balance equation. We have CH4 plus 2Cl2 will make CCl4 plus 2H2. We're not worried about the hydrogen, okay, because it's asking about CCl4. Okay, so we're going to take our 1 mole of CH4, and we're going to use the balance equation between methane, CH4, and chloroform, CCl4, carbon tetrachloride. So it's 1-to-1 ratio, so 1 mole over 1 mole, and then we multiply by the molar mass to get the mass of CCl4 that we should get if we had 100% conversion. So we should get 158 grams. That's our theoretical yield. And then we can take the mass of what we should have got. So this is actual. Where's my pen? Actual divided by theoretical, and then times by 100. All right, let's write that again. Actual over theoretical times 100. A over T, and that's our percent yield. And one of my students told me a little way to remember this. A over T times 100. I don't remember it though, but there's some way to remember it. But actual divided by theoretical. And so we get 54.2% yield. So I wanted to show you guys how to calculate that. Let's go ahead and look at our homework assignment. All right, let's look on Canvas and look at this real quick. And I took notes on this, so this should be pretty easy. These videos are so long. I tried to make it short, but it doesn't happen. Lots to talk about. All right, chapter 2, problem set number 1. So let's take a look at our questions. All right, number one, the following data were collected for several compounds of nitrogen and oxygen. And so here's our mass. This is the mass of nitrogen that combines with 1 gram of oxygen. So if you're looking at this and you've paid attention, I mean, this just screams law of multiple proportions, right? And it says it right here. Show how these data illustrate the law of multiple proportions. So how do we do that? Let's go here, new slide. I mean, if I did A over B, I got 1.750 divided by 0.875, and I get 2. And then I can do A over C, and when I do that, I get 4. When I take B over C, so every combination, I get 2. Now, even if you don't get a whole number, you should be able to multiply by something easy to get a whole number. And I've seen this in another example in this homework. In this case, we get whole numbers, so boom, we proved that this is the law of multiple proportions, right? All right, next one. Some of these I'll need to show work, some of them I don't. Write the symbol for the atom that has an ionic number 9 and has a mass number of 19. How many electrons and how many neutrons does this atom have? So if it has atomic number 9, it's fluorine, right? So here's atomic number 9, fluorine. And it has atomic mass of 19. So what we can do is we can take 19 minus 9 to get the number of neutrons, which is 10. And assuming this is a atom, it's neutrally charged. No, it's balanced out. There's no the number of protons and electrons is the same. So if we have 9 protons, we would have 9 electrons. Okay. Which of the following combinations of elements is likely to produce an ionic bond? Ionic bond is between a metal and a nonmetal. So metal, nonmetal. So it's A. These are both metals. These are both nonmetals. These are both nonmetals. So those don't work. These would form covalent compounds. This wouldn't happen. These are 2 different metals. They're not going to react together. They both want electrons. What are they going to do with each other if they both want electrons and they both want to lose electrons. So if they both have electrons and want to lose them, what are they going to do with each other? Nothing. Here's our snowman. He's going to break down. So this shows which thing? This shows the law of conservation of mass because you have all of the parts there. Okay, so it shows a snowman here, and then it's the same snowman, it's just in pieces. So you didn't create or destroy snowman. Okay, well, I guess you kind of destroyed him, but he's still there. He's just on his side in pieces. It's sad, but it's okay. That's what he gets. Consider the reaction between hydrogen gas and oxygen gas to form water. 2H2 plus O2 makes 2H2O. Which of these is a correct representation of this reaction? So we just want to find the one that has the right balance. So 2H2, notice that there's 2 H2s, 2 pairs of hydrogen, 1 oxygen, and then 2 water molecules, where each water molecule has 1 oxygen, which is red, to 2 hydrogen, which is white. So that's our balance equation. This one is not good because this is not H2. This is H4, right? You want 2 molecules of H2. So that one's not good. This one, you don't have water. This is hydrogen and oxygen. That's HO. You have HO. You don't have water. And then D, you have H2O2. You got 2 oxygens and 2 hydrogens. So here you have hydrogen peroxide. And this is a cool molecule where it's got a -1 charge. Oxygen is usually -2, but in this case, oxygen is -1. So it's a kind of a unique compound. Don't drink that. It's bad. So you can't drink that. You can drink water, H2O, but H2O2, it's bad. You can't drink it. Poisonous. Which of the following equations satisfy the law of conservation of mass? So if you look at each of these, this one's not balanced. Okay, why is it not balanced? I have 2 oxygens here, only 1 here. So that doesn't work. Over here, I got 2 chlorines here, only 1 there. Not balanced. This one, same thing. I got 3 hydrogens, 2 hydrogens. Not balanced. This one's balanced. 1 carbon, 2 oxygens, 1 carbon, 2 oxygens. So this is D. Number 7. The following data were collected for several compounds of nitrogen and oxygen. I'm gonna have to do this one on the thing. So here's our numbers. This supports law of multiple proportions. because we're given the mass of one element that reacts with 1 gram of the other element. Mass of one element, oxygen, that reacts with 1 gram of the other element, nitrogen. So let me look at this one. And the reason I want to show this one to you is because it's kind of tricky with the numbers. And then we're almost done here. So we have W over X, which is 0.5711 divided by 1.142. When I divide that out, I get 0.5, but I can easily make that a whole number by multiplying by 2. So I get a whole number. So that supports the law of multiple proportions. Yes, it's not a whole number when it comes out, but if I multiply by some easy number and double it, then it does make a whole number. X over Y is 1.142 divided by 2.284. If I do that, I get 2. That checks out. Y over Z is 2.284 divided by 2.855. I do that, I get 0.8. And this one was a little tricky, but I multiply that by 4, and that gives me 4. Wait, 0.8 times 4? That doesn't check out. Times 5. 0.8 times 5, and I get 4. Sorry. So I get 4 there. So if I multiply it by 5, and so if you're not sure what to multiply by, try a 1, then a 2, then a 3, then a 4, then a 5, then a 6, and just try 1 through 9 and see if you can get it to be a whole number. And you should be able to get it to be a whole number. And you guys get the point, so I can keep going, but yeah, we get a whole number for every one. All right, next up. Number 8. Let's do this one. The following data were collected for several compounds of nitrogen and oxygen. If compound X has equal number of oxygen and nitrogen atoms, what is the most likely formula for compound Y? So I think I was talking to one of you guys, I think it was Pei, about a problem like this. And what I read from this problem is that we can kind of determine the percentage of each element in the compound, but we can't find the exact compound from this data. So this is what John Dalton did with his atomic theory, is he could determine the percentage of elements in the compound from this data, but he couldn't really pin down the exact compound from this. Okay. But we're going to go ahead and find the compound with this because they're giving us extra information. So X is equal to 1 oxygen to 1 nitrogen, equal parts oxygen and nitrogen, right? That's what it says in the problem. So equal oxygen to nitrogen. So what is Y equal to if it has twice as much oxygen? Wait, let's go back to the problem. Let's read the problem. Sorry. If compound X has equal number of oxygen and nitrogen atoms, so I'm just going to say 1 to 1. Let's just say it's NO. What is the most likely formula for compound Y? Okay. So let's do the ratio of X to Y. 1.142 divided by 2.284. I think you guys can see that that is 2. So X has twice as much oxygen than nitrogen. Therefore, if X is equal to NO and Y, X has twice as much oxygen than nitrogen. So X over 2 is 2. So I think it should be NO2. And I'll double check this, but I think it should be NO2, but I need to check the answer key. But I'm thinking it's B, NO2. X has twice as much oxygen than nitrogen. X has 1 to 1. Yeah. So I'll double check this one, but I'm thinking B. All right, let's see what else we got. I need to look at that one. That one's a little slimy. Number 9, when 20 grams of calcium carbonate is placed into a crucible and heated, it's going to decompose into 11.2 grams of solid calcium oxide and carbon dioxide gas. So that means it's going to make 11.2 grams of calcium oxide. So that 11.2 is all calcium oxide. And then it's going to make carbon dioxide gas on the side, which will leave the container because it's a gas. It's just going to go up into the air. It's gone. There are several ways to represent this reaction. One of the most common ways is by chemical reaction. CaCO3 will make CaO plus CO2. And you guys saw this one on the test as well. So I hope this question helped. Another way is to draw it. So this crucible shown illustrates what it looks before any reaction has taken place. What will the crucible look like after the reaction has taken place? So here's our crucible with 20 grams of calcium carbonate. We want to show the reaction after, all right, but there's some points that we have to think about. The fact that the CO2 will leave because it's a gas. And so I keep seeing this 8.8 here, which is the 20 minus the 11.2 for the calcium oxide that we made. That 8.8 grams is not going to be shown. So A is not correct. D is not correct. And all that we're going to have remaining is the calcium oxide, which is 11.2 grams. So here it is, B. Just 11.2 grams remaining. All right, number 10. Which of the following choices consists of a pair of isotopes? If you look at each pair, they're not the same element. Well, this one's an ion, so this one's an ion, so that can't be it. These are different elements, so it can't be an isotope. A pair of isotopes would have to be the same element. All right, so it's this one, C, hydrogen. D is an ion too. So that's it, guys. Thank you. Sorry this was so long. Peace out.